Welcome back. This is Dave Does Math at Home. Today we're working on section 5.3. 5.3 is titled Trig of Any Angle. I used to hate that name, but I am warming up to it. It's actually a pretty descriptive title once you figure out what's really going on in this section. Before we figure out what's really going on in this section, I need to tell you about a couple triangles. These are the two really special triangles we're going to see a lot of in this section. This is a 45-45-90 right triangle, also known as an isosceles. Turns out I don't know how to spell isosceles. You'll have to trust me. This is an isosceles triangle. I'm going to write 45-45-90. There we go. No one even saw that. Perfect. This is a 45-45-90 right triangle. This has a very special ratio of side lengths. The basic ratio of side lengths is that if one of these guys is 1, the other has to also be 1 because it's isosceles. And if these two things are 1, you can use the Pythagorean theorem. 1 squared plus 1 squared is 2. So this side must be the square root of 2. If we want to scale this down so that the hypotenuse has length 1, which we do, using a hypotenuse of length 1 is going to help us out a lot in this coming section. So if we scale this down so that the hypotenuse has a length of 1, that means that each of these sides would be 1 over square root 2. But again, as we talked about briefly in the last video, 1 over root 2 has an irrational denominator, and hundreds of years ago mathematicians didn't like that. So the official way to write this number is as we should rationalize the denominator by multiplying this fraction by root 2 over root 2, and that would give us root 2 over 2. And then this side would be the same thing. Both of these are root 2 over 2. This is sort of the official way to write this number. For the most part, again, I'll repeat this. For the most part, I don't care about rationalizing denominators. If you're working on a problem, on a test or a quiz, and you have a radical in the denominator and you want to leave it there, great, cool. I don't care. I'm not fussed about it. The homework does want you to rationalize denominators, so you'll have to practice multiplying the top and bottom by the bottom to clear the radical from the bottom. The other thing that I am sort of interested in and I do care about is that in very special cases, like root 2 over 2, I do want these ones to be rationalized because they're so iconic. These numbers are going to show up over and over and over again. You're going to see these until you're sick of them. They're extremely common, they're extremely important, and in the interest of you being able to easily recognize them as soon as you see them as the important numbers, I want us to all write them in a sort of unified, uniform way. So we're going to use this and not this. So this is the 45-45-90 right triangle. It has side lengths root 2 over 2 if the hypotenuse is 1. The other super important triangle we're going to need to keep in mind is the 30-60-90 triangle. This one I'll start it with the hypotenuse being 1. We saw in the last video, the ratios on this triangle are that whatever, the short side is always 1/2 the length of the longest side. So if this is 1, this is 1/2, and then we can use the Pythagorean theorem from there to find out that the third side should be root 3 over 2. So that's the 45-45-90, and this is the 30-60-90. Make sure this is in your notes. We're going to be using this information a lot for the rest of these videos. So, now that that's in your notes and you can look at it as you like as we go through the rest of this material, we're going to get into the trig of any function, or trig of any angle part of this, which is the super exciting bit. The big limitation of trig, as we understand it so far, or I should say as it has been presented in section 5.2. 5.2 is right triangle trig. It's just about you get a triangle, you get some side lengths, you take the ratios of side lengths in the triangle. Those are your trig functions. The big limitation of that, as it has been presented so far, is that it only works on angles that fit inside triangles. So you could do it for 30 degrees, you could do it for 60 degrees, you could do it for 45. You could hit really, really thin, narrow triangles at the 80-degree range. You could hit 50s, 40s, whatever. You can hit all of these triangles, but the angles that you're working with, if the angles are going inside a triangle, these angles are inherently locked within the 0 to 90 range. We want these trig functions to work for much, much more than that. Ideally, these trig functions will be extremely versatile. Hopefully we'll be able to plug any number into these trig functions and get a value. This comes back to the idea of domain restrictions. If these trig functions have domain restrictions, if the only angles that work on them are between 0 and 90, then that's kind of just a pain. Every time we use one of these trig functions in anything, we're going to have to ask, are the angles in the right range? Do we have to do anything with this? What if you plug in a 100-degree angle into this thing that only takes 90 degrees? It's a mess. So the goal of this section is to expand this idea beyond triangles so that we can think, what would happen if you tried to take the sine or the cosine of a 100-degree angle? What would that look like? 100 degrees doesn't fit inside a right triangle. Geometrically, that doesn't make any sense. But maybe we can stretch this idea of what sine and cosine mean so that we can take the sine, cosine, and tangent of bigger and bigger angles. Or even smaller angles. Maybe negative angles. That would be convenient. Hopefully we can get every number covered. So that's the ultimate goal here. And we're going to accomplish this goal by using the coordinate axes. We learned in section 5.1 that you can put angles on the coordinate axes and that they go counterclockwise. So if you put a 45-degree angle on the coordinate axes, you always start on the positive x-axis, you go counterclockwise, this is your 45-degree angle. Using this 45-degree angle, we can drop a vertical to the x-axis. That'll make a triangle, a right triangle. In fact, this will make a 45, 45, 90 right triangle. So we can say that this hypotenuse is 1. That's going to be extremely convenient for us. I'll talk about the convenience of having a hypotenuse of 1 in a second. First, I want to talk about the coordinates of this point. Based on what we remember from our 45, 45, 90 triangles that we just put on the board, this length should be root 2 over 2, and this distance should be root 2 over 2. They're both root 2 over 2's, which means the coordinates of this point are root 2 over 2, root 2 over 2. That's the point you get when you put a 45-degree angle on the coordinate axes with a distance of 1. So, based on this point, I could ask you for the sine of, not of theta. I don't want theta, I want 45. In fact, I could ask you for this in radians. 45 degrees is pi over 4 radians. We haven't forgotten radians. We just took a break from them in section 5.2. They're coming back. 45 degrees is pi over 4 radians. And with this, I can look at the sine of this angle would be the opposite over the hypotenuse. And that is what is really, really convenient about having a hypotenuse of 1. Whatever the hypotenuse is, I have to divide by that number. And the very easiest, most convenient number to divide by in the world is 1. So throughout this section, I'm always going to be setting my hypotenuses to 1. so that I'm dividing by 1 when I'm getting these values, and that just makes it super straightforward. So the sine of pi over 4 will be the opposite, root 2 over 2 divided by 1, which is just nothing. The cosine of pi over 4, which is this 45-degree angle, degrees radians, is also just root 2 over 2. So the really convenient thing here is the sine and cosine values match your x and y values. Sine is your y value here, cosine is your x value here. And that's pretty handy. The tangent here would be root 2 over 2 divided by root 2 over 2. That would be 1. So this is our y value, this is our x value, this is the quotient y over x. So, we're going to take this idea and we're going to look at what happens if I want to talk about a 135-degree angle. 135 degrees does not fit inside a triangle. Can't be done. Doesn't make any sense. Or, I'm sorry, it can fit inside a triangle. Doesn't fit inside a right triangle. That can't be done. Doesn't make sense. But I can still create a triangle out of this angle by dropping a vertical to the x-axis. The triangle I get still has a 45-degree angle in it. The 135-degree angle is not inside the triangle, but it is the angle that is creating this triangle. And now from here, I can still look at the coordinates of this point, and they'll be the same values, because I've still got a 45-degree right triangle. I still want the hypotenuse to 1. So we'll have the same root 2 over 2 values. The difference is the x value is now negative. So we are now in quadrant 2, which means we'll get a negative x value and a positive y value. Those are the coordinates of that point. Which means now I can talk about the sine of 135 degrees. Even though 135 doesn't fit in a triangle, we can still talk about its sine. Because the sine is still going to be the y value, or more generally it's the y value divided by the hypotenuse. But if we choose to set our hypotenuses to 1 all the time, then it'll just be the y value. So the sine here is still root 2 over 2. The cosine of 135 will be negative root 2 over 2. And the tangent of 135 degrees, which is 3 pi over 4, if you're wondering. 3 pi over 4 is the radians here. The tangent would be this divided by this, which is negative 1. So, in some ways it just kind of doesn't make any sense to talk about the sine of an angle that doesn't fit inside a right triangle, or, sorry, talk about the cosine of an angle that doesn't fit inside a right triangle and get a ratio of side length that is negative. In some ways that's just kind of a bizarre concept that we probably shouldn't be doing. In other ways it's extremely useful and we're definitely going to do it. So these angles that don't go in triangles, we can still make triangles out of them using the coordinate axes. We can still get these points, and as long as we can get these points, we can find sine and cosine values. That's what this section is all about. We're going to go through a couple more examples, and then we'll switch to a new video. Okay, I want to look at putting a 30-degree angle in here. And again, I'll drop this vertical I want the hypotenuse to be 1. I want the coordinates of this point. The x, if this is 1, this should be root 3 over 2, and this should be 1/2. That's our special 30, 60, 90 right triangle. Those are the proportions there. Which means the x value of this point should be root 3 over 2. Y value of this point should be 1/2. Which means, I'm going to convert this into radians. This is pi over 6. Which means I can very easily get the sine of pi over 6. It's 1/2. Divided by 1 is just 1/2. Cosine of pi over 6, root 3 over 2. Tangent of pi over 6 is 1/2 divided by root 3 over 2. 1/2 over root 3 over 2, which is 1 over root 3. The halves cancel, which is root 3 over 3, because we're rationalizing those denominators still. So, you can get these trig values from this triangle on the coordinate axes very easily by using this as a y value and this as an x value and this as a y over x ratio. So this is a normal triangle. 30 degrees fits inside a triangle. Nothing wacky going on here. Until I ask us to do negative 30 degrees. Negative 30 degrees does not fit inside a triangle. You can't have a triangle with a negative angle in it. That is not how triangles work. But we're going to do it anyway. Negative 30 degrees means we're going clockwise from the positive x-axis instead of counterclockwise. We're still going to drop a vertical to the x-axis to make a triangle. We're still going to want the hypotenuse to be 1. This distance, or this length, is 1/2, but the y coordinate of this point is negative 1/2. This length is root 3 over 2. That's going to stay positive because we're still on the right side of the axis here. So now we can see that the sine of negative pi over 6 should be negative 1/2. The cosine of negative pi over 6 should be positive root 3 over 2. And the tangent of negative pi over 6 should be negative root 3 over 3. So this is another great example of using regular, normal, fits inside a triangle angles to explore what would happen if we put weird, bizarre, doesn't go in a triangle angles onto a coordinate grid and then try to figure out what the sine, cosine, tangent of those things are. That's what we're doing in this section. I've got one more example for us, and then I need to talk. We're already at 18 minutes here. Let me change to a new video for one more example, and then some general advice on these.